Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today I want to talk about two important notions. The first one is the notion of a group homomorphism, which is used to compare different groups and is a very important way of studying group theory. The other notion is that of a permutation representation. Now remember, the concept of a group was to study symmetry mainly, and the way we set that up was we looked at permutation groups and we abstracted the algebraic properties to get the notion of a group, and we looked at subgroups of these permutation groups, and we want to generalize this notion of subgroups of permutation groups to the notion of a permutation representation, and that's going to give us a little bit more flexibility to study groups and symmetry. Okay, so let's look firstly at this notion of homomorphism of groups. So basically you should think of this as a structure preserving map. Okay, so for example, when you look at linear maps between vector spaces, that's a map which preserves the linear structure of those two vector spaces. Here we have group structure, and the group structure is given by the group multiplication. Okay, so suppose we have two groups H and G and a function phi between them, phi from H to G. Okay, so we say it is a homomorphism if it preserves multiplication in the following sense here. Okay, so what's this sense here? That means that if you're given any two elements in the group, H and H prime, of course you can multiply them together to get a new element, H prime, inside the group, and apply phi to that to get an element of the group G. Okay. The other thing you can do is you can first apply phi to each of these group elements in H to get phi of H and phi of H prime. These two are now inside G, and since G is a group, you can multiply them inside G. So here you have an element of G, here you have an element of G, and if it's always the case that these two are equal for all possible choices of H and H prime, then we say that this is a group homomorphism and it preserves multiplication. Okay, so if furthermore this phi is bijective, we're going to call this homomorphism an isomorphism. And this is the case where essentially we think of these groups as more or less being the same, and basically this phi, which gives you this 1-1 correspondence between the two, is like a dictionary going from this group to this group here. Okay, so there's a real correspondence, and since it essentially takes the multiplication of H over to the multiplication of G, they're essentially the same group. Okay, so let's have a look at some examples of this to see how this concept works. Okay, and in the meantime, I'll also introduce some new groups. Okay, so the first one here is going to be GLNF. So here F is some field, N is a positive integer. And what this group is it's just a group of invertible n by n matrices with entries inside our field F. Okay, so of course this is a set, and to say that it's a group means that there is some sort of group multiplication here. And the group multiplication here is just matrix multiplication. Okay, so remember, if you multiply two invertible matrices, that's also invertible, and you can check that it's a group. So of course, matrix multiplication is associative. This group is closed under inverses and has the 1 as well. Okay, so there's existence of identity, the identity matrix, and an existence of inverses in this group. So the special case where n equals 1, we're just looking at invertible 1 by 1 matrices. Well, a 1 by 1 matrix is just a scalar. Okay, so often we abbreviate this to F times. Okay, F times just means the scalars which are not 0. Okay, so that's the special case GL1F. Okay, so we're going to compare these two groups using some function between them, and it's going to be a homomorphism. Let me show you what an example of such a homomorphism. It's the determinant. Okay, so if we're given an invertible n by n matrix with entries in F, A, we can take its determinant, and of course that will be some non-zero scalar. Okay, so it's an element in F cross or F times. Okay, so that's certainly a function, and I claim that this is also a homomorphism. To check it's a homomorphism, we just have to check that it preserves multiplication. So let's see that it does. So suppose we multiply two elements in here together. Okay, so two matrices A and B. Then we take the determinant of A times B. Okay, that turns out it is indeed the product of determinant of A times the determinant of B. Okay, So it doesn't matter whether we multiply first and then apply the function, the determinant function, or we take the determinants first and then multiply. Okay, so that's what it means to preserve multiplication. So we see that holds. This is a well-known formula from linear algebra. So indeed, this is a group homomorphism. Okay, let's look at another example, and in so doing also introduce some new very important groups. Okay, the first one here is the group of integers z. Okay, so as a set, it's just a set of integers. And now it's a little bit funny, the notation here. We have to give it a group multiplication. And here sometimes it's better to use a longer notation for it. So how do you put together two group elements a and b, so two integers a and b? Okay, mu of a and b is going to be a plus b. Okay, and to save confusion, we'll write the group multiplication as a plus. So often we abbreviate this to times, but then maybe you'd be confused to think that it's integer multiplication. Okay, so we'll leave the plus sign in there. Okay, so that's an example of a group, and you can check the group axioms easily enough. Okay, so let's look at another example of a group, and this is called the cyclic group of order n, which is also extremely important in mathematics. Okay, the notation for it is, I guess there are several notations for it. The one we'll use here is z mod n, and so this stroke is pronounced mod, and that's because this is the set of residue classes modulo n. Okay, so this is something you see in modular arithmetic. So it has n elements, 0 bar, 1 bar, up to n minus 1 bar. And that's what it is as a set. It's a finite set of n things. And of course, you have to also give it a group multiplication. And in this case, remember, you can also add residue classes modulo n. And we let the group multiplication equal addition in this case as well. Okay, great. So that's there are two groups. And it turns out that we can compare them using a homomorphism. Okay, so how does that work? So what's the homomorphism? Okay, in this case, what is it? So we have a function phi from z to z mod n. It simply takes an integer to its residue class modulo n. So that's certainly a function. And the question is whether it preserves multiplication. Of course, the multiplications in this case are both addition. So I guess we're really just asking, does it preserve addition? And that's quite easy to see that that's true, and hopefully is a fact that you already know. If you add two integers first, and then take the residue class modulo n, that's exactly the same as if you take a and b, their residue classes, and then add them inside here. So that tells you that it does preserve the group multiplication, and hence this is also a group homomorphism. Okay, so in this example here, this is quite an important homomorphism, and just to sort of emphasize how it's important is the following, okay? So what's a natural use for this group here? So there are lots and lots of uses for this, especially in number theory. And let me just give you one example. So for example, suppose you ask a number theoretic question like, is 6,006,006 a square? Okay, well, the answer is quite easy in this case. What you can do is you can look modulo 4. If you look modulo 4, you'll find it's congruent to 2 modulo 4. And of course, there are no squares which are congruent to 2 modulo 4, because if it's congruent to 2 modulo 4, it must be an even number, and hence the square of an even number. And if it's a square of an even number, it has to be congruent to 0 modulo 4, a multiple of 4 as well. Okay, so one of the uses of this sort of thing is here we start off with a question about integers being a square in the set of integers, and we can pass over to questions about being a square modulo 4, okay, in that particular instance. So we've forgotten information when we look at this group homomorphism. But the point is that sometimes when you forget information, that's not a bad thing, because what you've done in this case is the question of trying to determine something's a square here. That may require a lot of work because there's too much information. Sometimes you just want to remember the most important salient information, enough information to answer your question. So it turns out that if you work modulo 4, you can remember a small amount of information that's much easier to work with and easy to answer the question at hand. So remember, Group homomorphisms are the group analog of a linear map. So just as there are lots and lots of nice properties about linear maps, there are analogous properties for group homomorphisms. And I want to show you some of them now. And if you remember they're linear analogs, you should have no problems understanding these concepts. So the first thing that you know about linear maps is that it sends 0 to 0. If you have a group homomorphism, there's an analogous fact. It sends the distinguished element, the identity, to the identity. Phi of the 1 in the domain, so 1 inside H, is equal to the identity, the 1 inside the codomain G. Okay. Another thing that you know from linear algebra is that composites of linear maps are linear maps. So if you have two group homomorphisms and you can compose them as functions, then the composite of those homomorphisms is itself a homomorphism. Also, if you have a linear map, you can talk about two natural subspaces, the image and the kernel. And both these things have natural analogues for a group homomorphism phi from H to G. Given such a group homomorphism, we can consider firstly the following subset of G. It's just the image of phi, in the sense it's just the range of values it can take. It's a set of all phi h's, as H ranges over all the possible inputs in the domain. And that set is of course a subset of G, and it satisfies the closure axioms for a subgroup, and hence is a subgroup. That's the image of phi. Similarly, we can ask, is there a kernel of phi? Yes, there is a kernel of phi. So what's that? It's a set of all elements inside the domain which gets sent to the distinguished element in the codomain. So phi of H equals 1. Okay, if you look at all the solutions to this equation here, what do you find? All those H's, that's going to, of course, be a subset of this group H, and in fact, it's a subgroup, and it's called the kernel of phi. Okay, so these two facts that you know from linear algebra have their group analogues, and it's quite nice. The fourth property that I want to tell you about is a very simple way to get group homomorphisms, and that occurs whenever you have a subgroup of a group. So if H is a subgroup of G, then there's a very simple function that you have from H to G. It's called the inclusion, that just sends H back to itself. Okay, so that's called the inclusion map, and in fact in this case, since these two are groups, in fact, or H is a subgroup of G, this is actually a group homomorphism. So remember, this itself is a group in its own right. Okay, if you restrict the multiplication here to here, this will be a group, and this is in fact a group homomorphism, so we call it the inclusion homomorphism. Okay, so there are four nice simple facts about group homomorphisms, and they're quite easy to prove just from the definition, and in fact they're essentially the same as the proofs for the linear analogues that you see when you study linear algebra. Okay, so let's look at some examples to see some of the features that we see here, okay, and also to introduce us to more groups. Okay, so the first one goes from the group C cross to C cross, okay, and it's just raising some complex non-zero number z to its nth power. Here n is some positive integer, okay, z gets raised to the nth power. And it's quite easy to see that this preserves multiplication. So in other words, it doesn't matter whether you multiply two complex numbers first, say z times z prime, and raise to the power of n, or you raise those two complex numbers z and z prime to the power of n and then multiply. Okay, so given this group homomorphism, you can of course look at the image, which actually will turn out to be the whole of this C cross, and also its kernel. That's not the whole of C cross, and that's an interesting subgroup. Okay. Okay, so what is that? So they're all the things which get sent to the distinguished element in the codomain. So they're all the things where z to the n equals 1. Of course, that's just an nth root of unity. So we call this the group of nth roots of unity. Okay, and we denote it mu n. Okay, it has n elements inside there. Okay, so that's a very, very nice group with n elements. And we know another very nice group with n elements. Remember, it's the cyclic group of order n, Z mod n. It's also just the group of residue classes modulo n. Okay, and in fact, I claim that these two groups are isomorphic. Okay, and there's a natural isomorphism between these two. Okay, so I claim there's a well-defined group isomorphism as follows. Given a residue class A bar, okay, we can send this to this nth root of unity, e to the 2 pi I a over n. Okay, so why do I have to check that it's well defined? So Why have I included that term here? Well, that's because, remember, this is only defined modulo n, okay? You can change this by multiples of n. If you change the a by multiples of n, of course, you just change this exponent here by integer multiples of 2 pi I, which doesn't change this expression here, okay? So it's well defined. And of course, you can see that it's both injective and surjective, and it gives a bijection between the nth roots of unity and these residue classes modulo n. So the main idea here is that these two groups can arise in different situations, sometimes as symmetry groups, but sometimes in other parts of mathematics. But as far as the group theory is concerned, this isomorphism means that the study of one is equivalent to the study of the other. Okay? If I want to say, for example, study something about this group here, okay, I can use this dictionary and translate all these elements to the corresponding elements over here and ask the same question over here. Maybe it's easier to answer over here. Maybe it's something that you already know here, and so you automatically get an answer over here. Okay, so that's why the notion of a group isomorphism is very important. Okay, it's like a dictionary between two groups, so that anything you can say group theoretically about one, you can say group theoretically about the other one as well. Okay, so that's a very, very important example, and it's a well-known fact that's good to know. Okay, so what I want to do now is I want to go back to material in the first video about subgroups of permutation groups, since this was the way that we decided we should encode symmetry. Okay, and I want to generalize that in the notion of a permutation representation. Now that we have the concept of a group homomorphism, we can do that. So that's the following definition. Okay, so to get a permutation representation, we need two pieces of data to start off with. Firstly, a group and a set. So we talk about a permutation representation of a group G on a set S. Okay, and what is that? It's a third piece of data. It's a group homomorphism from G to this group here, the permutations on S. Okay, so that's what it is. And I claim that this is just a generalization of the setup that we saw before, okay, where we're looking at subgroups of the permutation group of S. Okay, so how is that the case? And that gives us our first example too, okay, of a permutation representation. Suppose G is a subgroup of a permutation group on S. Okay, so remember, if you have a subgroup, when you're in that situation here, this fourth part of the proposition tells you that you have this inclusion homomorphism of the domain into the codomain. Okay, so that always occurs. By the way, the special time when H equals G means that this is just the identity map. So the identity map is a group homomorphism. Okay, so in this case here, we have the inclusion homomorphism of G into the permutation group of S. And that's why this old setup is included in this notion of a permutation representation. But the point is that sometimes it's better to have this extra flexibility. And I want to give you some examples to show you how that's the case and how it appears in symmetry. Okay, so the next example I want to look at here is the rotational symmetry group of the cube. Okay, so let's suppose we have a cube like this one here. Okay, so I've got a cube, and maybe I'll do it like this. So what do I mean by the rotational symmetry group of the cube? Well, if I want to write out the cube, maybe mathematically, one way to do it is to write it out as, firstly, I take the integral from -1 to 1, and I just look at the cube of that. So it's -1 to 1, maybe an interval like this one here on the side, and you cross it 3 times. So this one, cross this one, cross this one. Okay, this one, cross this one, cross this one. Okay, so that gets you a cube. Okay, and the center of mass of that cube will be the origin. Okay, and you look at rotations which send this cube back to itself. That's what the rotational symmetry group is. It's a rotations A, so that just means an element of SO3, the special orthogonal group of dimension 3, such that A of C equals C. Okay, so of course that's a subgroup of SO3, and the elements of SO3, remember, that's a subgroup of the permutation group on R3. This is a very, very interesting group that can be used to study the symmetries of the cube, and can answer lots of interesting questions, and we'll see examples of that later. But let's try to get a feel for some of these rotations which live inside this symmetry group here. Okay, so the first one, and probably the one that you'll first think of, is to think about rotations. Of course, you need an axis of symmetry. So you can look at the axis of symmetry which goes straight down the top face, the middle of the top face, and you can just rotate by 90 degrees, or 180 degrees, 270 degrees, and of course 0 degrees as well. Okay, so that's one possibility. And of course, you didn't have to do that just through the top face. You can pass through the middles of two opposing faces, okay, and rotate by any of those angles. So you can use this vertical axis, the horizontal axis, or the one that goes in and out of the cube like this towards the board. Okay, but there are actually other symmetries as well that are going on. Okay, other rotational symmetries. So another one that you can have is you can look at opposite vertices. So you can look at this vertex here and this vertex here. And you can look at the axis that goes through those opposite vertices and rotate about that. Okay, so if you rotate about that, you can get a rotation which sends this cube back to itself. Okay, so here it goes like this. Okay, that's an example. Okay, that's an example. Maybe I'll bring it up closer. Okay, so you can see. Okay, so that gives you another type of rotation, and they correspond to axes which go through vertices. And I hope you can guess what the last type of rotations that you can get, which are elements of this rotational symmetry group. So we've looked at axes through the middle of faces, axes through the vertices, and of course you can go through the middle of edges as well. So suppose we take two opposing edges, like, so we'll take this edge here, okay, this edge here, and this edge here, and we look at the middle of them. We've got an axis there, and we can rotate by 180 degrees like that. Okay, and that's also a rotational rotation which sends the cube back to itself. Okay, and it's pretty easy to see actually that these are the only possible rotations which send the cube back to itself. Okay, if you have an axis of symmetry, it has to go either through a vertex, the midpoint of a face, or the midpoint of an edge. Okay, so that's the key thing, and they're the three types you get. Okay, that's fantastic. Okay, so certainly you have the usual permutation representation, GC, just is included inside here. Okay, but as you do one of these rotations, one of the things that you might see is that it swaps the faces around. Okay, so we can look at the set F of faces. This just has 6 elements inside it. And each time you perform one of these rotations, right, what it will do is it will swap the position of the faces. Okay, so it will permute the faces. So each A inside this GC will give you an element of this permutation group of F. Okay, it's the permutation of the faces. And of course, what is the group multiplication here and the group multiplication here? The group multiplication here is composition of these permutations, and the group multiplication here is just composing matrices, which corresponds to composing maps from R3 to R3. So it's also composition. Okay, and when you think about it that way, it comes pretty clear that, of course, this map here preserves multiplication and hence is a group homomorphism. So here we have a rather interesting example of a permutation representation. So basically the symmetries of the cube, of course it acts on the cube, but the thing is that it also gives you symmetries in terms of the faces. Okay, so you have a permutation representation on the set of faces as well. The last interesting example I want to show you of a permutation representation involves the dihedral group Dn of order 2n. So remember, this is just a symmetry group of the regular n-gon. So the point I want to make here is that, of course, this symmetry group permutes the plane and also the regular n-gon R, but it also permutes the orientations of this regular n-gon. So how do we think of the orientations of a regular n-gon? What do we mean by that? Well, let's pick a regular n-gon like this square here. Okay. So one way to think of the orientation is just a choice of a normal sticking out. Okay, so that's an orientation. Okay, another way to think of it is you just draw an orientation or a direction on the regular n-gon. So here I've got this anti-clockwise direction here. Okay, and I claim that the symmetries of the regular n-gon, they each induce a permutation of this orientation. Okay, so let's see how that works. So suppose the element of your dihedral group that you're looking at is a rotation. Okay, if you rotate, okay, it doesn't matter how you rotate, okay, the normal will stay pointing in the same direction, so the orientation is preserved in that sense. And this anti-clockwise direction that you see here remains going around anti-clockwise. Okay? Now let's suppose instead you have a reflection. If you have a reflection and you have the orientation given by a normal, of course, when you reflect, it will flip the normal, so it goes to its negative. So you swap the orientation in that sense. Also, in terms of writing it as a direction here, you can see that this anti-clockwise direction gets swapped to the clockwise direction. Okay, so one way to think of this orientation is just a set of anti-clockwise and clockwise directions drawn on your regular n-gon. Okay, and this symmetries of this regular n-gon will permute these two. Okay, so this is a rather interesting permutation representation. Okay, so this is naturally the symmetries of regular n-gon, but it's going to produce symmetries of some smaller thing, in this case just a set of orientations. And here we've actually lost a lot of information, okay, because there are only two ways that you can permute these two things. Either you leave them as identity or you swap them around. Okay, but that doesn't mean that it's uninteresting. Okay, so what it allows you to do, for example, is you can talk about the kernel of this group homomorphism. Okay, so you've lost information. The only thing you've remembered is what you've done to this orientation, whether you've flipped it or not. And what have you forgotten? You've forgotten basically all the things that get sent to the identity. These are no longer distinguished. Okay, so these elements, they're of course form the elements of the kernel of phi. Okay, and that's the rotational subgroup, the subgroup of rotations inside here. So one way to study a group such as this one here is you can try to use a homomorphism and homomorphisms to compare it with another group like this, okay, and study this group here. Now you've lost information here, and this is a much simpler group to study, okay, so you can study this one because it's easier. But how much have you forgotten? You've forgotten this, so you should also study this as well. And to study this group means to study these two parts and how they fit together to give you the whole. Okay, so that's one way of studying a group. And this type of setup allows you a way to approach such a study. The final thing I want to say is that this example here is very much related to a group homomorphism that I told you about earlier. So that's the group homomorphism from GLNF to F cross, which just takes an n by n invertible matrix to its determinant. So both these groups, of course, you can also think in terms of symmetry, okay, just in this example here. So this GLNF, what's that? How is that related to symmetry? These are invertible n by n matrices, and so they correspond to change of basis matrix. Okay, so one of the things that you see in linear algebra is very often you'll find that one basis is just as good as any other. There's a symmetry between all the bases. Okay, so unless you impose some extra conditions or have some extra data, okay, if you just have some vector space that's n-dimensional, okay, one basis is as good as any other. Okay, and to study the symmetry, to say that, to express the fact that one basis is as good as another, just means that you want to look at all the change of basis matrices. And so that's this set here, GL and F. And in fact, you want to think of it not just as a set, but also as a group. Okay. So the key point is that, well, which are the orientation preserving symmetries here? They're the rotations. So they're the ones of determinant 1. Okay. Rotations have determinant 1. And which are the ones which swap the orientation? They're the reflections, and they're the ones which have determinant -1. So in fact, this is actually a generalization of what goes on here. So we can also use this setup to study what's going on with the symmetry of this regular n-gon. I hope you enjoyed this adventure in pure mathematics.